the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to another episode where today we have special guest Dr. Zack Wolske on with us today, a postdoc fellow here at the University of Toronto, and actually Parker's teacher for linear algebra. So that's really cool. So interestingly enough, you might notice the background's a little bit new. We are actually, for the very first time, inside a U of T building recording the podcast. And here with us today, in person, is Dr. Zack Wolske. So, Zack, you want to introduce yourself to our listeners for a little bit?
Hi,
Who
sure.
are you?
So I'm a postdoc in the math department at U of T. That means I do some research related to math things, I do some research related to math education things, and I do some teaching.
Math education, definitely very important for the future.
I hope so.
Of math.
So, before we actually get into the podcast, we have a quick introduction. Quick intro to the episode. As you know, we share the news for the podcast. So this week, we have, we're almost at a very special number, almost at 300,000 downloads in total.
That's crazy.
So
That's
thank you
crazy.
so much for downloading the
That's crazy.
podcast. Also, we are almost at 17,500 followers on Spotify. So if you're listening to this podcast right now, make sure to hit the follow button and even go on YouTube and subscribe to this video. If you
You know what you should also do on YouTube, though? You should comment.
And why would you do that?
Why should you comment on one of our YouTube videos, though? Comment of the week.
That's why.
So the comment of the week is a weekly comment picker on whoever comments on our videos. And last week we have Paul. And Paul says, just wanted to say thanks for doing this podcast. I'm a 32-year-old tile settler. I've listened to every episode and look forward to every new one. Thanks for making my mind stimulated in a job where monotonous tasks are the norm. Keep it up.
Thank you so much.
Thank you, Paul, for a lovely comment. Any other news we want to get to? I think
that's all.
I think that's basically it. So we can get into the nitty-gritty of the podcast with the classic question, as we always do. You also
I did
know
some
this.
prep.
You also know this. So, Zack, let me ask you, what originally got you into the field of mathematics?
Okay, I think this is a hard problem.
It is.
Call it a problem, not a question.
I was thinking about it, and I just keep going further back in time.
Mm-hmm.
Then, I could say, oh yeah, doing my PhD, that was really when I was doing mathematics.
Mm-hmm.
But before that, doing my undergrad, I switched over from engineering into pure mathematics. And even before that, my experiences of childhood when I'm solving puzzles and doing these books of things that are like Sudoku, these type of logic game puzzles, maybe that's what got me into math.
So
I
kind
have
of
some
like
kind of game.
Was it stimulated by your parents, or was it from you?
Oh,
you
no,
went out
they
and
didn't.
bought your puzzles.
I mean, someone gave them to me. I think a lot of times my grandma, something for me to do.
Puzzles always.
They were puzzles that were logic related. So sometimes logic grid, these people live in these houses and how are they related and what do you figure out? And sometimes things where you're filling in numbers, but never anything that was school math.
Never
Always
anything,
I get the same feeling from doing a Sudoku, where the numbers don't actually matter. What matters is if this is true, then this other thing.
Kind of
has
like
to happen.
intuition. You can apply your thinking without really having a good knowledge of the scenario, right?
I think the opposite.
You think I would think it is more related to just you thinking logically and less of knowing. Is that not
that's less intuition.
I agree
Isn't
with
that
that.
more
yes.
intuition?
I think it's more you think a little bit deeper. It's not I see the answer. You go one step at a time and you say this follows logically from this, and then you keep going.
Absolutely.
Okay. That's also a
Alright.
valid way to think about it. Sure.
My intuition would be I just put whatever numbers anywhere. I need a grid full of numbers. But really, I need
guess that's
follows the logical rules.
Yeah.
And my guess is I don't know that they're correct.
So that's probably where I can see how that can be a starting point for a lot of mathematicians, with base logic. Like, because I mean, like a little bit of philosophy in there too, like a little bit of why do these numbers work this way, and why does this block in Sudoku work, kind of thing. Like a simple question like that. You know, you can extend it, always generalize it to higher orders when you get older. But just starting with that base,
anytime.
or
Anytime.
I guess anytime.
You
But
always get older, right? In the
Yeah.
future. So
I guess. Well, so we've established that the Sudoku probably got the math into you.
The
But, like,
logic.
or
the logic,
behind
right?
the
The
logic.
logic.
The logic
and
into
totally divorced from math. So,
So
like,
I guess, I guess. So
when I
also
did
logic
math
very
in
similar.
school,
Yeah.
I would do well. And I think mostly it was from just having logic.
Mm-hmm.
And not really like familiarity with numbers or anything, but people would say like, you're good at math. And I go,
Yeah, I guess.
Are you
guess.
familiar with Olympiads?
tests.
Are you familiar with Olympiads?
so until grade 5, I had no kind of contest anything. I moved to a new school, and there was a dedicated math teacher, and she said, hey, we run this math contest club. Do you want to come and try these out at lunchtime once a week? And so I did, and it was all like older students, grade 7 and 8, and we just, work on things that were kind of like puzzles.
Yeah, that's
And I
basically
thought, this
what
is
they
great.
Are. Yeah.
And then I did the test, and I did great, and I was like the top scorer in my region.
Wow.
I was
Oh,
like,
wow.
nice. What's that mean? And then
No, wow, that's actually
you get a
really
little
impressive.
prize.
Yeah.
You get some money, and I went, cool, I'm in.
Cool.
Let's do this
cool.
again. Then when I was in grade 7, this sort of screwed up all my math education. I was in a split class, grade 7, 8.
Okay.
The teacher noticed I understood the math things and that I would also understand the grade 8 part. So we just said, why don't you just do the grade 8 test? You can get the grade 8 credit early.
Mm-hmm.
Have a spare or something next year.
Why not?
And I said, okay, sounds fine. We had a parent-teacher interview. I talked to my parents. He was like, you should be doing more advanced math. And they were like, we don't know any. What can you do? And he was
Okay.
like, we can offer grade 8. And they were like, cool. We're in. Will it cost us anything? No, we're in. Then my grade 8 teacher said, well, it's silly for you to do grade 8, and I'm not going to have you sit here and do nothing all class, so you're going to go over to the high school and take a grade 9 math.
Wow.
And she arranged for that to happen, and thanks, Miss Darlington. From then on, I took math with people a year older than me every year. So I didn't know anybody in the math classes. I would do math before my peers. I would never talk to them about math. And it really derailed my math experience.
Mm-hmm. So that's kind of a part of it, a big part of it.
But for sure, that was an aspect that made me go, okay, I can do math.
But when you were doing it with the older kids, like, did that inspire you, or did that demotivate you that, oh, my friends aren't here? Or were you thinking like, oh, I'm in this big boy class? Like, what way did you think about it?
I guess
Like glass half full
I
or
was
glass half empty?
thinking, I get a free credit. I get an extra spare in grade 12.
That's how you're thinking.
I'll get this done now so I don't have to do it later. That math classes were not very inspirational at all.
Yeah, so it wasn't really oh, I really like it. It was just, hey, I'm good at it, so I'm just
No,
gonna
it
do
was
it.
a thing I could do.
Okay,
Yeah.
okay.
I never really
So the
liked it.
passion for math hadn't still really come out yet, or was it there? It was just never in school.
I guess, it was there and it was not in
It
school.
was just not in school.
I would still write contests.
I can see a lot
I
of
still
people
did
with that.
well
Yeah.
in these contests. I had I'm from Durham region, which is a little away from Toronto, and does not have exceptional math students. So being on the top of my region wasn't like, oh, I'm crushing it. But I got, in my last year in high school, I got an invitation to a national math camp. That's we picked 50 people from around Canada. Everybody comes to Ottawa.
Oh, wow.
You hang out with other
From
high school
Ottawa.
students, and you get to do cool, fun stuff with these math professors from University of Ottawa. And that was great. Then I was like, oh, math is fun.
Yeah.
You can do these interesting things. There are other people who also have this logical way of thinking about puzzles, and you get to have fun.
Yeah,
So
I
that's
think when you meet people
a
like
start.
that, yeah, for sure. But being in the position now, especially as a math educator, and having been in the situation where you were so interested in math as a kid, but weren't pushed in school, I think this is a huge question. But I mean, this is also very general because every teacher has their own response for this. But is there a particular thing that you saw in your education where you're like, I just wouldn't do it this way. I just wouldn't teach it this way. Because being an educator yourself right now, would you be like, oh, I've changed my way of teaching to this because I think this gets out that passion in those people?
This is relatively new for me, but I think if I would change anything in any education, it's to get rid of grades.
That's very powerful.
That's
a very powerful statement.
Grading students and assigning grades, and we see this especially in math when we have some kind of dichotomy of right, wrong, that you get the answer on the test or you don't get the answer on the test, and if you don't get it, you're a failure, and it really pushes people out of math.
Mm-hmm.
And that not having grades does not have this effect. So
not
my answer to your big
grades-
question of what would I change, I would get rid of grades.
So get rid of grades as in like no exams? Or like still exams, but you're not graded, or like you get feedback, or like
we would have to think about, why do we want to have an exam? What's the purpose of an exam?
My always, because my thought of an exam is in a real life scenario, you're gonna have like a deadline, you're gonna have like a stressful situation.
Certainly.
So you're gonna have a period in your life where you're gonna have to apply probably a lot of the things that you learned in like a 40-minute period. You're
Do
like,
you
oh
think-
shoot, I don't know how realistic it is because I'm still in
40 minutes?
I don't know. Maybe
Do
not.
you think
Maybe not.
at any point in your life after university, someone will put you in a room with some paper and no other external tools and ask you to solve some problems?
I guess that's a big thing too. The no external tools thing is also a very controversial, like, why do you
But I think, to be fair, like, exams are an okay way of saying, like, oh, how well did you actually like absorb some of the material? Like, it's
do you
some
believe
way.
that? Do you believe that like an examination is a good way to test if a student has understood the material?
Parker said an okay way.
I said okay.
He said okay, but I'm asking you now.
I don't like exams. I'm just saying that it's a valid way to be like, yeah, I can do some of these questions that are related to the material because I understood it.
What about you? I really want to know your thought on the
I
exam.
think that's certainly true for some students. I think there are students who, under non-test situations, can fully explain and answer problems. And then when there is a test, that like some anxiety kicks in, that your brain freezes, and you go, I don't know what to do. And for those students, they are very mumuch being punished by having exams that do not consider them.
Yeah.
It's a little sad. Well, it's sad that they're.
But we
But
just have to think about, what do we need, what do we want from exams? And if it is a student to demonstrate that they understand something, are there other ways that we can do this?
Mm-hmm.
Yeah, that's actually really powerful because like the whole, I mean, this is such a taboo and like, you know, such a common thing to say, like the whole education system is so bad because it's been like everything has changed, modernized in the last 200 years. Education system been the one thing that stayed almost the exact same, you know, with like the teacher in the front of the board teaching 30 kids.
The lecture.
Or like
30,
the lecture.
I wish.
30.
I mean, the idea.
250, give me, yeah.
I get,
Yeah.
okay, sorry. The university definitely much bigger, but the idea of the lecturer-student interaction is always basically the same, has been the same. So I guess like changing it up, like I believe it's a country, Finland or Sweden, one of those countries that has got rid of grades completely and has actually seen quite a large increase in the productivity of its citizens because of literal removing grades from high school.
How do you measure that, though?
Because I believe the way that they did it, or the study that I was seeing, was like percentage of like CEOs or like successful businessmen or something like that in the area. Or
So sometimes I listen
it was
to this
some
pod,
measure.
and Ray throws out a lot of unsourced.
Yeah,
things.
no, believe me, I
So
will.
for this one, he's going to put
Very
a link
true.
in the description.
I'm
Ray's gonna find the
okay,
link.
I'm gonna,
You don't
I'm
have to
gonna
find it
the
now,
link.
but it's going to go in, so we can go check it out. I want to know about this.
I
I'm
do
very
wanna know.
interested to hear about this.
There are definitely because I saw this whole video dedicated to changing like education systems, and it was talking about like this one country that had removed grades and it had seen like more successful stuff. It was either, again, I don't want to pull it out because I will cite it, but I just wanted to mention because like you're talking about grades and you're talking about how like the effect on grades. So I wanted to say that it's happened before.
I'm aware
in
of some
places.
studies where this happens way more locally. that in a certain region or in like a district in the US where they can control effects of grades, they can just remove grades. And they traditionally do it in rich, white, suburban areas, and they notice, hey, it has a big effect, everybody does better. But yeah, absolutely.
Yeah.
There's a lot on the scale to say grades are not helpful.
Like assignments, though. Still agree with assignments.
I don't know. What do we want from assignments?
Assignments, I would say, is the same thing, though.
What
It's
would,
like you
what
still
would
have
be
a
the
deadline.
evaluation then? Just have like an interview, like a one-on-one interview?
Why do we need an evaluation? What's the purpose of the evaluation?
No, just to be like, you didn't waste your time in this class and you absorbed some of the knowledge.
So something I do in my class is ask students, what did you absorb from this class? What did you learn? Tell me about it.
Mm-hmm.
If they can't tell me anything, then I would go, okay, this class did not go well for you.
That's it?
But mostly they can tell me some things that they can do.
But is that all that needs to be like tested? Is if you can.
So officially, the university requires certain things. But in terms of like an education for math, I mean, we can ask like Paul, hey Paul, what do you want to know? Do you still have, in the future, what do you want to know? What do you know now? Where are you going to go with this? And we don't need to think of math education as stopping after high school or after a university course ends. Mm-hmm. You take your last math course and then what? You never learn any more math? No, you get to say, here's what I do know, here's what I feel comfortable with, here's what I want to know. And then you can set yourself a plan of how you're going to learn.
That can be like any learning pattern can follow that, though.
Absolutely.
Right? Because I think that's super powerful, because a lot of people only think that, hey, I can learn this if I'm in university, or I can only do this if I'm in like, no, really, like, yes, it's probably a better, mode of, because I guess they're like, you have deadlines, they're legitimately teaching you, it's not on your own time, like there are a lot more restrictions, obviously, and pros and cons to both, but like having the whole system put onto, like, you don't necessarily need a university to learn.
Yes.
Right, is the point, is basically
you can learn on YouTube.
We should provide a lot of resources.
Yeah.
But there are a lot of options of learning other things about math.
So is that what you want to do with like your
boy.
career? Is just
Don't ask me about
to change?
I should have pre-interviewed this part. I don't know. What I'm finding out is there are a lot of institutional issues where I can't do the best teaching because I must.
Yeah.
Like I say, I don't want to give grades. I must give grades.
Yeah.
If I'm going to get paid for the course, I have to submit grades.
Yeah.
Does-
So, yeah, I mean, the change has to be, it can't come from one person, basically. It has to come from, I guess it could.
The
At
system.
the very top.
Yeah, the system. No, but the system needs to be like, okay,
Yeah.
this makes more sense. Like the whole. It can't just be. It can't just be like, or it can also be one university that adopts a system like this. That then changes. They're like, oh, shoot.
That's still a tall order,
They're-
though.
No, but that happens so many times where like, oh, they do it this way. You're like, oh shoot, they're doing a really good job. Maybe we should do this too.
Yeah.
Like in Finland or Sweden or something.
Yeah.
Yeah, like that's the idea. Also, I was doing some severe research. So
Severe.
severe in the last 5 minutes. But okay, so there is a very different education system there. I don't think it's no grades, but it is a severe lack of them. Like there's no homework, or there's a lack of homework over there, and the way that they mainly push their kids not to go to school for grades. Like I can link this whole article, but like they push their kids not for grades, but just to go there and learn, which is very similar to what you were saying. Like you're just going at the end of the day to know more than what you went in with, right? Which is, I mean, at the end of the day, the goal is cool. Is it not? Just to learn more, just to keep your mind always activated and to know what you want to do in the future, right?
Yeah, I think so.
Always activating. So that was very, I guess not a tangent. I guess I was still talking about it, but like a little interested on the on the university life a little bit. What about like the postdoc life, just personal a little bit? Because I know, or not even the postdoc, but even just the doctorate, and then moving on to the
my
postdoc is
PhD,
really cool.
I did twice. My undergrad, I said I went from engineering, I switched into math.
Yeah, that's a very interesting choice, because engineering, I would think, very, like, you would like a different stream, because engineering is, like, very hands-on, right?
Absolutely.
And then math
I
is
mean, I
just
went to university going, I want to do hands-on stuff.
Yeah,
I
math
like
just
building
got
things,
completely-
I like making stuff.
180, right?
This is what I want to
360.
be doing. I found out it was a lot of business-related things
Engineering?
and a lot of...
Business?
Absolutely.
Really?
Yes.
I didn't know that.
That a lot of the work is selling the product.
Oh.
In engineering?
Produce, absolutely.
Wow.
And that
Wow.
quite a lot of university research is paid for by military, weapons, people who want to build better materials to do destructive things. And I said, I will have no part in this. And so I dropped out of engineering, but I didn't have anywhere to go. And I moved around. I thought I would do applied chemistry. I thought I would do some applied math because I like computer science-y things. And I took a course on mathematical problem solving that was open for basically anyone. There was a science credit, but didn't have any prerequisites. The math that I had taken, you'll be familiar with these. It was like equivalent of like 135, well, actually like the engineering math,
Like first year calculus.
and like
Yeah.
235.
Second
Yeah.
year calculus.
A second year calculus, but like no proofs. I never wrote any proofs.
Yeah.
I took that course and it really changed what I was going to do. I loved it. It was a lot of logic and just thinking about puzzles. We used this book by Paul Zeitz, The Art and Craft of Problem Solving. Highly recommend. It's amazing. Then I just take all the math courses now.
Wow.
So in third year, I took 10 math courses.
Wow.
Oh my.
I just went, flip the switch, right? Do them all. In fourth year, more math courses.
Wow.
So just math, all math.
Which one was your favorite?
I went into which one was my favorite?
They're
I
all
guess
time.
I should say
all-time
number
favorite.
theory.
Number theory.
Oh, okay.
Number theory sold me. I went, I'm very interested
So
in this.
number theory was a third, fourth year?
Number
Fourth?
theory is a third year.
Third year course.
And then more number theory came later.
Yeah, I would
in
assume like
fourth
number,
year.
like it would be specializing
We
in
have a
probably fourth.
specialization type.
So, I mean, in all of this math, I mean,
Maybe I should say what's
We must-
number theory about.
no, yeah, no, for sure, for sure. I mean, we're still dabbling in the education section, but one thing, part of the podcast, obviously, the math and physics podcast. So the question has to be asked: was there any physics courses?
I took a physics first year.
Engineering.
absolutely.
No,
It's
but I'm
engineering.
saying any. No, but engineering.
It's,
It's
engineering
physics. It's
No, I-
physics.
It's taught by a
But
physics
no,
prof.
I guess so. But when I'm saying physics courses, I'm saying like, okay, yes. I guess engineering can be like classical physics. But I'm saying, did you take any like very like theoretical physics courses like thermodynamics or like
No.
or electromagnetic or electrodynamics? Anything theoretical? Because I don't.
It's
usually-
interesting me you call those theoretical.
No, because when I think of physics, I already think of it as very application based. So when I say theoretical, I'm just like, okay, what can be used on paper versus what can be done in person? And when I think of application based physics, I just think of engineering. I know that's not exactly true, but that's just what my mind goes to. I just think of where can I apply the physics that I've learned when I'm making something, like that's the way my mind. And when can I apply the theory of what I learned? Anytime I'm doing anything on paper. So everything non-engineering in my head just goes into the theoretical physics part. What do you classify as theoretical physics? Would that not classify as?
Well, I'm not
theoretical
sure.
for you?
So a lot of results from theoretical physics are secretly math results. Where I would say I do know some things about maybe quantum mechanics or maybe thermodynamics. As part of a teaching course that I'm taking, we go and observe other people. I went to see someone who was teaching a class specifically thermodynamics for engineers, third year engineers. And I understood what was going on in that course. But I understood because I have a math background.
I was just gonna say the math background probably helped you like
If I
quite a
know
lot.
things about vector spaces, then I secretly also know about the specific vector space that they would care about in physics.
I can see where in quantum mechanics you would probably just sit down in the class and understand everything.
I hope
I
that's
think
not
so. No, I think you would though, because a lot of that level of quantum mechanics and a lot of higher level physics is based in forms of linear algebra, right? And like understanding like vector spaces and like metric spaces in general. Fields like the quantum field is literally one of the, or the gravitational field is like one
true. Yeah,
of
I
our
think
most.
this is not a field, right? That's my understanding.
No, but the well, we still represent it as a metric field, though, as like the metric tensor. Even in because technically the gravitational field is not a field, but the only way to actually deduce how the space curves around stuff is by measuring the metric tensor, is by measuring stuff with the gravitational field. Okay. So usually there's still fields on top, but like the whole foundation of math I would assume be super crazy in any physics course, because you would have at least like the fundamentals understood.
That's true.
Right?
That's very true.
Right? Don't you think so?
I don't know.
I think
don't
so.
know
I guess
the
no,
culture.
for sure. No,
I definitely think you sit in a quantum mechanics class, you'll be like, huh, okay.
Yeah.
Like I follow it, maybe maybe the physics, but like you follow the math, like how one state evolves to the next, for example, is all just transformations in algebra that you would, totally just know what to do for. I would assume even have a better understanding than some physicists in a lot of.
Yeah, because I'm taking physics 356 right now, which is quantum 1 technically, because last year was intro to quantum, and the second unit was just all pretty much linear algebra, but in Dirac notation, and so, but
Which
it was
I
like
learned recently is backwards.
yes, so. It's if you already know all of the things that we're learning in linear algebra right now, it's just new notation, but it's all the same stuff.
No, because Parker was even talking. I mean, we talk a lot about the classes we do together and stuff, and he was talking to me about how like the linear algebra course like perfectly fills in with his third year quantum mechanics and like all the relationships between both the classes. So like definitely a mathematics background would help in any real form of physics, I would think. Right?
Yeah. Also, it's kind of surprising because when we were in first year, we were learning math from our physics courses.
More math
before we learned them in math, and so that was very backwards.
Like we learned integrating and stuff, like, or at least not learned, but like whoever hadn't taken like the 137, because the integrating was in the second semester. Yeah. Like in the very first semester of physics, we were already thrown into like some integrating concepts and stuff. Yeah. And people are like, okay, I guess we're doing this now.
Yeah.
Like that was just something we had to do.
I also had this experience.
Yeah.
Yeah, no,
exactly.
Very, very similar. Very similar.
And it's very much a part of like the education thing of like we need to certify that someone can do a certain thing. Mm-hmm. And to do this, solve problems in physics, you need to know how to integrate something. Mm-hmm. And for a mathematician to integrate something, you need to understand the definitions first. Mm-hmm. So we don't want to put it first term.
Yeah, that's true.
But if you don't, you can't do any problems in physics.
So then they just say, here's how you do this in physics, and then you're like, oh, I'll go watch some YouTube videos and
I guess that's a lot of the. I guess figuring out is a lot of, because in your doctorate experience, I don't believe we've actually gone through the doctorate experience. Yeah. So in your doctorate experience, did you go through
one first? What do we know about number theory?
So
and how can you find out more?
Did you do your doctorate in number theory?
Yes.
Okay, go for it. Okay, I'm very excited. What is
number theory?
What is it?
What is number theory?
I don't know.
Theory of numbers.
Theory of numbers, yeah. Which numbers?
Because numbers are so... The weird thing about number theory, in my opinion, again, no knowledge here, but just my understanding of it, numbers are the most obvious thing when people think of math. What's math? Numbers. Even though that's not at all what it is, that's what people think of. So you say something like number theory, you're like, oh my God, this is like the most important thing in math. Like that's...
And it is.
And it is. Okay, see, I didn't know that.
Is that opinion or just fact?
Because
that like number
theory you're a number
like,
theorist.
I think I can make an argument for it.
A little bias. It's a little biased opinion, but sure.
So numbers. The numbers that we care about are natural numbers. We want the counting numbers. And maybe we want 0. And maybe we also want integers. So we want things like, what is going on with the numbers 0, 1, 2, 3, 4, 5, 6, 7, and maybe like -1, -2, -3, -4, whatever.
So not like the reals. We're just dealing with
We
the.
do not care at all.
You don't care about
That's
rational
interesting.
numbers?
So rationals are like friends of natural numbers.
Yeah.
That
But-
sometimes to figure out something about natural numbers, it's easier for us to work with rationals. Because rationals form a field, which means we can divide. We can't divide by natural numbers and stay inside the world of natural numbers. Same reason that we want to look at integers. Integers let us subtract. So we can subtract 2 integers, we get another integer. We can't subtract natural numbers and get another natural number. So
Wait, what? Why? What's it?
Like 1
sometimes one's
minus
bigger than
5.
another.
You're
but
no
like
longer
10
a natural
minus
number.
3.
Yeah, but it's the general
Sometimes you
case.
can't-
Oh, the
Something
general.
like
Okay, you're saying generally. Okay, cool, of course.
Yeah, we want something that always works for us.
General, yeah.
Mhm.
So then we try to figure out, like, what are some properties of natural numbers? Do you want to give a pitch of where can your listeners find more about natural numbers?
Well, the best place to find more about natural numbers. And that's brilliant. This episode of the podcast is sponsored by Brilliant. If you liked all the stuff we're talking about on the podcast today, you will definitely like the courses that they have to offer, ranging from stuff like linear algebra all the way to number theory. They have quite an abundance of courses, especially in the coming months. They did install a lot of interactivity with their new math modules. So if you want to learn, if you want to challenge yourself, Brilliant's always a great way to do it. They've been a long supporter for us, so you already know we love to use it. So if you want to use Brilliant, go check out brilliant.org/MPP for a 20% discount on your premium subscription for the first 200 people that click the link in the description below. Now back to the podcast. Yeah, just continue.
You just do it later?
Yeah, we're just gonna do
Let
that.
me pretend you did the whatever, like. Okay, let me pick this up. So the brilliant problem of the day for today was in number theory was to take the numbers 1 times 2 times 3 times 4 times 5 and figure out what's the last digit of this. We stop at 9. So multiply all the numbers 1 up to 9. What's the last digit? I want you to tell me how you figured it out.
So we started just, well, I started just actually multiplying them in my head and seeing what happens. And I noticed that they were all even. So I first made the guess that that the last digit was going to be an even number.
Similar. I thought, hey, there are 4 evens. There's, well, any number of odds. And I know that odd times odd makes odd. And we know that any other combination of odd and even make even. So we have a bunch of evens that make an even. We have a bunch of odds. So at the end of the day, we have an odd times an even, which will end us up with an even. So I think we were both on the same page, and we're like, okay, we know it's even.
After a little
But
bit
after
of guidance,
yeah,
we found that 2 and 5
we're both present.
could be separated from the rest. And then it's like, oh, it's just some number times 10. And then we're like, any number times 10 is going to have 0 as the last digit.
And that was our way of thinking.
Yeah.
But definitely guidance was required.
Your way of thinking is brilliant. That's great.
It's
It
brilliant.
works.
It's brilliant. I love your pun.
We want to know what's the last digit, so we care about what's the remainder when we divide by 10. And
Oh, yeah.
a thing that we study a lot in number theory is, can we figure out what's happening with natural numbers by looking at just the remainder when we divide by something small? Because there's so many natural numbers. There's such a huge amount of them. We can't write them all down. We need to figure out some patterns. So we look at small cases. We're saying like, okay, what happens 1 times 2 times 3? I'm always getting something even. Is it always going to be even? And then we figure out some reason why that conjecture is true.
That's such a cool way of thinking. I love this way of thinking. Yeah.
And so Ray tells us, look, the only way you can get an odd by multiplying numbers is if they're all odd. So if one of them's even, you multiply them together, it has to be even.
Yeah.
That's our proof.
Yeah.
Now we're doing math. We start with some little puzzle. We try some small cases. We make a conjecture. I think it's always going to be even. We come up with a proof. Why is it always even? And now we know We narrowed it down. It's
we
going
do.
to be
It has to be.
Gonna be
I think my proof would be to just take the 2 out and be like, this thing is something times 2. And
That's
then,
great.
That's actually that's
and
actually
then-
a really
yeah,
nice way to
and
think
then-
about it too.
yeah.
Because I was thinking when you said take out the 5 and 2, I was thinking why can't you take out literally
literally
any other number
anything.
too, and you can say very similar things about the other ones too.
right. We can take a bunch of them out.
Yeah.
So let me do a little follow-up on this one. What do you think the sum of the digits is for this number? If I take 1 times 2 times 3 all the way up to 9, it has a bunch of digits in it.
Oh.
If I add them all up individually, I get something. If I keep doing this process, if I take any natural number, I add up all the digits, I get another natural number, it's smaller.
Mm-hmm. Of course.
So I do it again, it gets smaller again. At this stage, if you're a mathematician, you ask, why is it always smaller? And then you can give a proof.
I think that's
Figure out
pretty,
a-
I think that's a pretty straightforward proof. Is it actually? No, I don't know if it's a straightforward proof. It's a straightforward way of thinking that it's smaller.
Yeah.
Sure.
Like it's pretty obvious, but I guess the
So we should
proof.
conjecture it's smaller.
Yeah.
We should,
Smaller.
well, I think we
Yeah.
can say that.
I'll let you know it's true, but come up with
Yeah.
a reason why.
Good.
So eventually you get down to just a single digit number. What single digit number do you think you get from this?
Is it the same every time? Oh,
No,
wait.
no.
Oh, I've heard it's like 9 or something
No.
for some reason.
No.
No, that's not true though. Because
Literally
you can
impossible.
take
Any other
14
number.
or
13, 12, like so many counter.
But I heard there's a lot of numbers that go to 9 for some reason.
It's probably some conspiracy garbage. we
Yeah,
watched.
it probably
Yeah,
is.
it's-
It probably is.
Okay, no, realistically though. So you said, and keep adding up the numbers until it gives you some one
Yeah,
number.
let's do a little baby example.
Wait, would it? Can you describe
Would
that
it-
number?
Yeah, would it not depend on the properties
Yeah,
of the
it would
number that
just-
you start with?
Sure. So the number that we start with is going to be 1 times 2 times 3 times 4
Oh,
times
that
five.
one
that one.
specifically.
9 factorial. That's our
Oh,
number.
Okay.
What number do you think you get then?
I have no idea. I don't know how to start.
Like maybe if we like really sat down. I don't even know how to really
How would you start
that,
without
know?
actually like
No,
seeing
like
what
there's
it
definitely
is?
no, because I mean it's a pattern, bro. Like it's obviously a pattern. Like you just have to just put down a few numbers on. Like we're not gonna do it now, but I'm saying put down a few numbers on paper.
Yeah, why
And I
not?
think if we can start, we can see some kind of pattern, like 1 2 3, 1 2 2, 1 5 6, in random numbers, and just see if that gives you anything. You know, I'm
Okay.
just spitballing here for random numbers, but
Okay.
So it starts 1 and then 2. And then 1 times 2 times 3 is 6. Great.
6, still 6.
Then 24. Now we have a 2-digit number.
Gives you 6 again.
Gives us 6 again. Any conjecture so far? Always 6?
No, always even so far,
Always even.
except for 1. But yeah.
yeah.
I multiply by 5, I get 120, and that gives me 1 plus 2 plus 0
Oh,
is
no
3.
longer.
Odd number.
Now there's just no pattern.
There's no pattern. We're going to be in trouble.
They're factors of 12
They're all factors of 12.
or 6.
Or 3. Why would you say 12? You always go to the lowest. 3.
No,
I mean, you can.
They're still.
They're all valid
they still are.
descriptions,
But
right?
don't start with the highest.
I mean,
you
if
know?
the next one is 4,
Okay,
then I'm in
okay.
the money.
Yeah, you're right.
Let's
you're
look
right.
at the next one. So the next one, 720. 6 factorial
Oh,
gives us 9. 7 plus 2 plus 0 is 9.
So something to do with 3? No, but then 2 and 1.
Oh wait, I feel like this is following like some kind of like remainder thing, because it's like increasing to a certain level and then goes down, and then I feel like it's gonna go up, and then I feel like the next one obviously is gonna be lower than 9, cause
Okay, so conjecture. The next one is lower than 9.
yeah, cause
And everybody watching on YouTube, go
Put it
and
down in the
calculate.
go and calculate.
Put it down
What
in
are
the
we at?
comments.
1,
No,
2,
what do you
3,
think?
4, 5, 6, 7 factorial. You can go calculate what's 7 factorial. I'm going to try to do it real fast. I got 5,040.
Well, you just did that. Wow.
5 plus 0 plus 4 plus 0 is 9.
Oh.
Didn't go down.
No, it didn't. Okay. So
But we can disprove this we can disprove a conjecture, right? We find some other example.
Yeah,
We
just
thought-
proving is light is
Yeah.
very easy. Just
From
one
9, it's going to
counterexample.
go down. It didn't go down.
So we just disproved. That's wrong.
I'm seeing 0 pattern, but they're all divisible by 3 except for the first 2.
Except for the first 2, they're all divisible by 3. That's a conjecture.
Yeah.
can we show they're always divisible by 3?
So assume.
Ray, you told us before we started a trick that you've used.
Oh.
The divisible by 3.
Yeah.
You just you're supposed to add up all the numbers, and then if the sum is divisible by 3, then the number is divisible by 3.
Okay,
But-
so we add up all the digits. If the sum is divisible by 3, the number is divisible by 3.
There's no way that's true for all.
What?
For all, if you just keep going, eventually you're gonna sum to something that's not divisible by 3.
No, if you have any number and you add their things, and
Their digits.
no, I'm not saying continuously add. I'm saying you add it one time. Wait.
I know, but I'm saying in our case.
Yeah. That's
I'm
a
saying
rule.
in our case, we're eventually gonna stumble upon a really long number that at some point when you add the digits, it's not gonna be divisible by 3.
No.
At some point.
It's literally a rule that I learned in school.
No,
It's like a
I'm not.
theorem.
No, I'm saying what you're saying is true.
Okay.
I'm saying what in our case, you're gonna get some random number. It's gonna be, for example, 1, 2, 5.
Oh, like you're saying we're gonna get one
And-
number here.
Yeah, and
divisible
that's
by
not
3.
gonna add to
Oh.
something that's divisible
Well,
by
that-
3.
Let's chase
That
this
ruins your
out, though.
conjecture. Then
Let's-
your
hold on.
whole conjecture was that
Yeah, I know.
one of the numbers all the numbers are. Gonna
I know,
be
but I'm
divisible by
saying it's
3.
not gonna be true for like a following number.
Are those numbers all going to be divisible by 3?
In the future?
Like if we want to use Ray's rule, we need to know, is the number divisible by 3 or not?
But for that, we would have to know the whole thing that we were talking about in the first
Yeah.
place. How do you know? How do you add? How do you know the sum of the digits?
Well, how do you know if a number is divisible by 3? Because here we are in number theory again. Here's a really important concept. We have unique prime factorization. If I take any natural number, I can write down its prime factors.
Mm-hmm.
And that tells me everything about the divisibility of that number.
Mm-hmm.
You took 1 times 2 times 3 and you said there's a 2 in there, so it must be even.
But does that tell you anything about the divisibility of the sum of its digits?
Well, let's chase this one down.
I think that's the whole.
I think
that's
it
the
does,
whole,
maybe.
I think that's the whole.
So we have this one piece. Okay, I'm not done with this. Are these all multiples of 3?
So far.
Will they continue to be multiples of 3? Here's my conjecture. They're always multiples of 3 after 2 factorial. So 3 factorial, 4 factorial, 5 factorial, 6 factorial, all multiples of 3.
Wait, literally. 1 minute. Isn't that like super obvious though? Because you can just take out everything
No,
and just
this
leave
is
a
the
3 on the
sum.
end.
This is the sum. You sum the
You're
digits
saying,
first.
oh yeah.
You have to
You're
s-
Hold
talking
on.
about the sum
Not
right
connected.
now. You're not.
Yeah.
No. But oh yeah, you're talking about the sum. You're talking about
Just
the
the product. Is
Oh.
the product always divisible by 3?
Wait, we just.
No,
Oh, wait.
just the
No,
product, that's what I'm saying.
no. We just stumbled onto exactly what you were saying. You said if a number is divisible by 3, then it's the sum of the digits is also divisible by 3.
Yeah.
But we
But that's
already
exactly
know it's
what we're
divisible by
Oh
3.
yeah, we already know it's divisible by 3.
So we got a
We
theorem.
already
Right?
know.
By 3. Oh my god, that's so stupid.
It's not stupid. This
No,
is
it's
No,
funny.
I
No,
know,
it's
I
funny that
guess,
we
yeah,
realize right now.
The realization.
I also want to say, like, everything's obvious after you've thought of it.
Yeah.
That's so true. That's so
Yeah.
true.
Right?
Yeah, no.
A thing that I love in math is these aha moments of something where you can go, and the light bulb
Yeah.
turns on, and
You're
you're
like,
like,
oh.
now I get
No, that's
it.
just so obvious. No, yeah,
No,
I guess, because
You
we were literally
said
saying
it the
that.
whole
We were literally
time.
saying that the whole time.
So if the product is a multiple of 3, then the sum of the digits is a multiple of 3.
Yeah.
Mm-hmm.
So that makes sense.
And then you can sum the digits again. And you can do it again. So whatever this last number you get is, it has to be a multiple of 3.
Oh. We only have 4 choices. No, 3.
Wait, so is that like some fundamental property?
Yeah. I actually saw proof that like thing was true. That the sum, if it's divisible by 3, then the sum is also divisible by 3.
How did it go?
I forget. It was a long time ago. But what he did is he went through like how to check if something is divisible by 2. That's pretty easy. But then when you get to like 7 and 4 and 3, he showed like
7
proofs
is very
for why it's
complicated.
true. Yeah.
7. What the hell?
There's a rule. It's hard though. Like it's,
7? I
it's
swear,
hard.
no, because I remember because I had my initial education in India, and we had like all these tips and tricks for like math multiplications, and I swear 7 was like the only one where we didn't have a tip and trick.
That's probably
I
true.
think 7 was
There is
the
one more.
only one.
There is
But
one.
There's like a trick
Yeah, there is.
to find if any number is divisible by 7.
Yeah.
Really? Shoot.
I'll
Well,
find it.
we didn't learn it.
I can link you a little graph where you chase the graph around and it tells you if it's a multiple of 7 or not, based
wait.
on the digits.
Really?
I'll send it to you.
That sounds very interesting.
But yeah, 7 is special. And in number theory, we want to look at things like this, like how come?
Yeah, this is a really cool
How
number
come
theory
7
question.
doesn't have a nice rule? How come these other numbers do have a nice rule? Like,
7's always been a little bit of a outsider.
why?
It's always been.
I would look at this pattern of the sum of the digits is a multiple of 3, means the original was a multiple of 3, and go, why? What's the property of numbers that's making that happen? So number theory, we just look at properties of numbers.
Yeah, because 3, yeah, no, I can definitely. I think the fact that we've been through proof courses and like rigor courses is getting our brains thinking in such a level like synonymous with like this level of like thinking, like having questions like this. Because I see a lot of our friends who haven't taken proof related courses don't even think like this. Like, you have a question on the board, or like the professor shows you something and you're like, okay. But we're like, no, wait, why does that make sense? A lot of times I see this, and then like simple things like this, I can see just a simple difference in people who have taken, and we say this so many times to all of our listeners, if you have a proof course that you can take it. Because it just gets your brain thinking in this way, which is so different.
And I think
in
you
my
can do it
opinion.
with a lot of stuff. Like, I was talking about these puzzle books when I'm a child. Anything where you have something where you can look at patterns and you can ask, why is that happening, can help you with it. Just get in the habit of asking why.
Why is such a physics question? But I
I
guess
mean,
you can also translate it.
It's also
to
a
math.
question for
It's a
literally
question
anything.
for literally
It's a scholarly
anything.
question.
Yeah. It is. A scholarly question is the right way
Yeah.
to say it. A very powerful question, but clearly, I mean, it's what all mathematicians get to where they are, right? So yeah. So continuing on
I
number
think
theory.
it's how a lot of
Yeah.
academics get where they are. We want to do
Asking-
some
asking
research. We
more.
want to ask, why is that the case? Like, this is coming up in math education as well. I want to know, why do we have tests?
Interesting. Why
And
do
then we have to
that?
dig into,
Yeah.
we need to collect some data. We need to look at some small cases. We need to figure out some patterns and then make some decisions based off of that.
I mean, the same way that like technology evolves over time, and we look back and we're like, why did they do it this way? And okay, I'm glad we're doing it this way now. I think education is going to get there at some point. It might take a long time, but I think someday there's going to be like a way better way of doing things.
I mean, people are asking now.
Yeah,
these
exactly.
questions, right?
The questions are being asked, but when it's actually going to happen, it's going to be like, oh, obviously we should have been doing it this way the whole time.
Do you think that we're gonna be forming a new way of doing math though? Because I think when you say like new way, I can definitely see like, forms of science being assisted with new forms of science. But math, again, you can correct me if I'm wrong, is so fundamental that like the thoughts, like ever since like the 15th century and even before, are still basically being carried on, are they not? Or is just the way? No, I'm
No,
just wrong.
we have radically changed
Okay, never
how
mind.
we think about mathematics.
Never mind.
Oh,
never
well,
mind.
think about the Veritasium
Exactly
video.
the
that
video I was
came out.
thinking of right now, because there's I don't know, but so it's a very famous YouTuber, Veritasium, also very recently dropped a video where he talks about how mathematicians, the original invention of the imaginary number to solve cubics.
Cardano's formula, sure.
Yeah,
Yeah.
Cardano's formula to form cubics.
Yeah.
And that video basically not only took you through the math of it, but also through the history of math. And in that, we kind of saw like the way that people were thinking about it. And I'm just thinking, yeah, obviously it's a different way of thinking, but like the fundamentals are still there. Like the way that they
No, but
thought
I
about
think-
like a cube.
But I think
The way that we think about a cube is still changing today.
Oh, in what way?
Wow. Shoot. That's crazy.
This is going to come back to number theory.
Yeah.
But I want to
Of course.
say, in this course that I'm teaching right now, it's a vector space course. And we
Linear
give
algebra, second year linear.
second year linear
Yeah.
algebra.
Yeah.
And we give axioms for a vector space. Like, what does it mean to be a vector space? Those axioms were first written down in 1888.
Really?
This is very new.
Wow, that's actually...
This sort of
That's
method,
very-
like axiomatic method of thinking, all of your definitions from analysis are from like late 1800s, early 1900s. Everything about calculus with epsilon delta is very new. We have even more modern new things.
But that makes sense because I think that is a lot to do with interpreting the problem. Because I think maybe the point you're trying to get at, again, correct me if I'm wrong, but like not the fundamental has changed, but the way of interpreting it has changed. Or
I would say literally the
fundamental has
Yes.
changed. Okay, never mind.
One
The
thing,
idea
I was
of
wrong.
axiomatically defining objects. This is something that is sort of done in Euclid's geometry textbook, but was not really carried
Because I would
out.
think something like epsilon delta is like, okay, it's literally just a limit, or no, I don't even think limits was a Isaac Newton thing. It was just integrals, straight integrals. What's an easy way to understand derivatives? Okay, limits, let's create that. Let's easier way to understand that, epsilon delta. So again, my thought would be the way that we, are advancing with math, are interpreting it in a better way. Or are we creating new fields as well as we're going on? Because I don't know really I guess because I'm just so wrapped up in my world of physics. But I guess, yeah, of course it would apply to math as well.
Yeah.
Like new fields all constantly evolving, I'm assuming, yeah. So that would be like ever changing, and like your interpretation of that would also change over time.
Absolutely.
I think the reason why I thought of the video was because he said that like when this whole cubing problem was happening, they hadn't even had like the modern algebraic notation.
It was
yet.
all words.
It was word
It was
problems.
literally words. They were just writing down
so I
math
was
as
like-
words.
Which, now, this is the thing to make a distinction of, in Europe, they were not using modern
in
algebraic
Europe.
notation. But in Western Asia, they absolutely were
Oh.
using algebraic notation.
Wait, really?
Wow.
This is where algebra comes from.
Oh, I did not know this.
Wow.
Oh, wow.
Wait,
Okay.
Western Asia?
So Western
Now you
Asia
want
started.
So in India, pretty much.
Well, yeah. Like,
I mean, regions of India,
Yeah.
Persia,
Mm-hmm. Wow.
absolutely.
I would think who are the famous guys in that region, man? I don't know.
This is a problem, right? You don't know.
Yeah.
So
And this should
so
be
embarrassing.
much more in the history of mathematics, that we do not just hear about European mathematicians and what did some white guy do with something
Yeah.
that he
Yeah.
took.
Yeah.
Yeah,
A lot of it
half
is
of
stolen.
them.
A lot
Half
of it is
them,
stolen.
man. Like literally, like so many of them.
You know about Fibonacci numbers.
Yeah.
Do you know
Oh no!
Fibonacci
no,
just
no.
stole the whole textbook
No,
No, I didn't know that.
from Africans
No.
who were using books from India?
No.
What?
Your Fibonacci numbers should really be called Pingala numbers.
There's no way.
Or maybe Hemachandra numbers. Hemachandra wrote a textbook that explained a lot of properties of Fibonacci numbers, of this sequence, 50 years before Fibonacci was born.
No way. That's so sad to hear.
No, that's good to know.
What do you
though.
mean?
No,
There's
it's
no
good
way.
to know,
That's
but
good
I'm
to
saying
know.
it's so sad to hear that big names like that did that.
Absolutely.
Like the Thomas Edison thing. When I first found out that whole thing was just it was just like some fancy patent like some stuff that he did. I'm like, come on, that's how you get your name?
I think here's another place where you should be asking why.
Yeah.
Like, why are these the people who we know about?
Yeah.
Why have we heard about
I never even
Newton
thought of that.
and Leibniz? And why have we not heard about all other mathematicians
Yeah.
in the world?
Yeah.
Very concentrated to a few.
Well, I think
regions.
Newton's
Okay, Newton is in a world.
He did a
difference.
lot of stuff.
Newton is different though. Newton is different. Also,
I got bad
Leibniz-
news for you about Newton.
No.
No. There's no way.
This is
There's no
gonna-
way. You have bad news about Newton.
Maybe it's a different podcast.
Wait.
No,
I
just
need to
briefly.
know this now. We need to know this.
Oh, so Newton would never have shared his work on calculus if Leibniz was not publishing his work on calculus. Newton had written a lot and refused to show anyone anything. He used his results to show off, to solve sort of contest problems of the time,
Oh,
but he
just
used
have
that-
but
the
did
upper
not tell
hand.
anyone how he was doing any of it.
Wow.
He was not at all interested in teaching and learning and research in math. He was interested in prestige. He had himself appointed the president of the Royal Society of London and England, the people who are sort of decide which things are scientific results that are notable. And when he found out that Leibniz was publishing things about calculus, he published his own work that he had planned to keep hidden, maybe forever, we don't know, but he had no plans to publish it.
Wow.
So he published this book, Principia, and then he asked anonymously for the Royal Society to make a decision about who invented calculus.
No way this guy was that.
And then as the
Oh
president of the
my.
Royal Society,
He gave
he
it to
wrote the
himself.
decision that said it was Newton. This,
Oh my god.
so this result, this happening,
No way, man.
now you might go, okay, Leibniz, maybe he didn't care. Leibniz basically like lost his job over this.
Wow.
He had been appointed by the king to do like math-related things. That guy found out that he did not deserve credit for this thing that Newton was hiding, that Newton had credit for it officially from the Royal Society. And so he took away his patronage, and Leibniz no longer had a job.
There's no way
But
this guy did.
it could be true though that Newton did it first.
Newton absolutely did do it first.
Yeah.
No. I mean, I don't think that's what's the
No,
takeaway
but
from
the
story.
problem is that he did
Yeah,
keep
that
it
he
hidden,
did that.
Yeah.
Right. And then follow-up problems of
Follow-up.
like starting fights with the people over it. Right? That
Wow.
he did not need to have this big dispute about who invented calculus. He could say, here's my version, look at the other version, they're all good. They all help us out with learning math.
Yeah.
But he said, no, I want the prestige.
Yeah, it really puts a
My way is
stain
the
on
best way to do it.
him. Damn, that's not very glorious.
No.
Not a very glorious Newton ending. Well, destroying some of our legends in our heads.
Yeah, I
Thank you
got
for that.
Feynman up next.
Oh no! There's no way. There's no way, Feynman.
Okay.
There's no
we
way.
do-
No,
we have
this
to
is not
hear
happening.
this. We have to hear this.
No,
No,
I
there's
mean,
no
we should
way.
put it somewhere else.
All right.
But
Feynman.
Feynman killed a lot of people.
What?
Okay,
I mean, Feynman worked on the
not
nuclear
actually
bomb,
killed.
right?
Oh,
Okay,
well,
okay.
yeah.
That,
In
like,
that way.
Developing weapons for military to use on people.
But if you think about like the whole military bomb thing, like the whole like that would have happened regardless, in my opinion, because nuclear energy would have been discovered one day.
According to the physicists who worked on the problem, they were the only ones in the world who could do it.
Well, eventually, even if they didn't do it.
Maybe.
I guess you can never say.
You
that.
can never
You
tell,
can never
but
really say that. I guess.
What we
My-
know is that they did do it,
Yeah.
and what the effects were of that.
Mm.
But also, Feynman, just in his personal life, is a
No,
creepy misogynist.
he was definitely
Like,
a pretty
there's
wacky
no reason
guy.
that we should know
Like,
about this guy.
He's not like yeah. I know like a fun. He used to play bongos at a strip club. I love talking about that. Just a funny thing about Richard Feynman.
So why are these our go-to?
Why are these our go-to
heroes?
people?
Yeah.
The guys who are misogynists and tall and white? How come? How come all of these guys? What do they have in common? Anyways, that's in the in the math education world. We want to talk more about history of math. We
No,
want to
for
have
sure.
more people say, "Oh yeah, loads of people are doing math all the time for different reasons. It does not necessarily have to look like this one way of doing it." And what can we learn from each other in this area?
That's the level of math that you want, though. Like, not unfortunately always.
I mean, yeah, this is just what I try to spread to other people.
That's beautiful, though. That's beautiful.
Quick
Like,
question. Who are the heroes of number theory?
Who are the heroes of number theory? I guess Euler.
For sure. He's
So-
a big one.
Leonard Euler, he is a big one in that he made a lot of the questions about number theory. He solved a lot of the questions about number theory.
Made and solved.
And then he made it something, I guess he has had an effect on why do I think like number theory is the most important math field.
Why do you think?
No, that's an interesting take.
Yeah.
So we have these like big structural things in math. We have the area of algebra, we have the area of analysis, we have topology, we have geometry. And each of those sort of asks questions about themselves. They have like motivating problems. And they provide sort of methods of solving problems. So you can think of like an analytic style of proof, uses certain techniques and certain methods, and maybe answers a question about analysis, but maybe answers a question about algebra. Then we have these fields of number theory and combinatorics. And combinatorics has a lot of techniques, and it has some questions that are just combinatorial questions. But a lot of times the techniques are used to solve questions in other areas.
Combinatorics is so useful. I'm also in statistics, so like combinatorics is like
Absolutely.
huge.
Yeah.
So
Huge.
very, very useful things versus number theory. Number theory basically just comes up with problems. It does not have techniques. It takes techniques from all the other fields.
So it doesn't produce problems itself.
Oh,
is
it
what
produces plenty of problems.
Okay, okay.
It does not
No
produce
techniques.
methods to solve
methods
problems.
to solve them. It just uses the methods from already known stuff.
So then from like a meta-analysis of if I looked at a society, a group of people who were studying a bunch of things, and some of them create and solve their own problems, and some of them just create problems and get solutions from other areas, to me that means the people who are studying algebra and analysis and topology and geometry are also interested in number theory because they are applying their techniques to answer number
Right.
theory questions.
The rivers are flowing.
Everything flows into number theory.
Yeah.
So
Okay.
I look at number theory and I go, it has a lot of interesting questions. Why are the primes doing what they're doing?
Yeah.
It does not give me answers. And to get some answers, I go to maybe analysis. So we were talking about what are different prime numbers. Maybe we'll talk about like what makes a number a prime.
Mm-hmm.
But we started
that's
with-
very deep.
We can have this list of prime numbers, right? You gave me 2, 3, 5, 7, 11, 13, 17, 23, 29, 31, 37. We did a little conjecturing. They're mostly odd after 2. They're all odd.
Yeah.
So I want to know, related to like, if I look at remainders when I divide by 10, I learn about the last digit. Here, if I look at remainders when I divide by 2, I learn even or odd. We know they all have the same remainder when we divide by 2. So what about 2 to the 2? What if I divide by 4?
Oh, is that why you asked? Oh, because you took the power. Oh, that's an interesting. Okay. Okay, now I actually get why you asked that. Or okay.
Aha.
Okay.
So for me, like the structure of natural numbers, they all have unique factorization, so I can think of them as being made up of primes. So the number 2 is just 2. It's a prime.
Right.
The number 4 is really 2 2s.
Right. So every number you just look at its decomposition and you say like, what are the
Into your
groupings?
primes, into your
What are the
primes.
different groupings of?
No, I
prime
remember
numbers?
like prime factorization in like some
Yeah.
young grade where like we had to do and you have to represent it in terms of like the exponentials of the primes. It's like 2 to whatever, 3 to whatever.
Absolutely.
Yeah, absolutely.
But here's an interesting question. Why do we care about primes in base 10? Like, what about different bases?
That's super cool.
Yeah.
That's super.
So a prime doesn't know about a base.
It's prime in every base?
Can you talk a little bit about, I don't know if everyone knows, just what a base is. What's the difference between base 10 and 12, for example?
Sure.
Or just a little
Yeah.
bit for.
Yeah.
So when we write down an integer, we're usually writing digits. And intrinsic in this is that they are base 10. When I write down 124 to mean 124, I'm saying I have 1 10 squared, I have 2 10s, and I have 4 10 to the zeros. And then if I write down any number, I can think of the units thing as being 10 to the 0. I can think of the next digit up as being 10.
And then just
The next digit as being 10 squared, 10 cubed, 10 to the 4, however big I want. We didn't have to pick the number 10. We can pick a different number as a base. So we can write something like base 2. You might be familiar with binary. There, the unit digit is a 2 to the 0, and then a 2 to the 1, and then a 2 to the 2, and then a 2 to the 3. So the number, so let me write down like 1101 in binary would mean I have 1, 2 to the 3. I have 1, 2 to the 2. I have 0, 2 to the 1s. And I have 1, 2 to the 0.
Yeah, adding numbers like this is so weird.
And then if I put them all together, I get 8 plus 4 plus 1. So that number was really 13.
Yeah, that's just because we're not used to thinking in that way. So
of course.
when we see 13, we think of 13, but when we see that number, we just
Right.
we can't
1101 doesn't look like 13 to me.
Yeah.
Not at all. Yeah.
It's a different representation of this number, and whatever base we choose, the representations will look different. But that number 13 will be a prime no matter what. So what do we mean by primes? What is a prime? We were trying to come up with a definition, and it turned out to be a little tricky.
Yeah.
The best way I think we came up with it is,
Well, so it's an integer, first of all.
Yeah, well, first
or
of
a natural
all,
number.
It's a natural number that is divisible by 1 itself. That 1 in itself. We know, like, that's like the...
And
well,
has no other prime
no other
factors.
Well, yeah, so it's only divisible by 1 in itself.
I guess I can't use the definition of prime.
In the prime, no. So it's divisible by 1 in itself.
And that's it.
And it's natural.
And what do we mean by divisible?
Divisible as in it's an integer number of divisibility. Like it's not.
No,
there's
no remainder.
Integer
There's
multiple.
no remainder. That's the way to
or
say it.
there's
That's
no
the way to say
remainder.
it. There's no remainder after the divisibility.
And also, we're not talking about negative numbers.
We're not dividing.
You
by
can't
negatives.
factor negatives out of the number.
Okay.
Because like the minus plus 1, of course.
Yeah.
So my pitch is going to be, there's a lot of ways we can think about primes. And I love this one of, you can't divide it by any other number. That you can divide it by 1, or you can divide it by itself, and you can't divide by anything else. So I'm going to say, that's a perfectly good definition of a prime. We can have it. If we talk about divisibility, it doesn't matter what base we refer to, right? So you gave a definition. You never said we have to write it down in a certain base.
Right.
If we have a definition that doesn't depend on the base, that means those numbers with that property does not depend on the base.
Right. I would imagine, though, that... Okay, maybe not. Maybe I'm just like intuitively thinking that a number in binary would have different factors, but that doesn't really make sense because it's all the same. It's like just...
Yeah, how do you factor
It's a different way of saying the same thing, so you're just saying the same thing at the end of the day.
Well,
So, no, that doesn't make sense.
when you said, what do you mean by a factor, you never had to talk about the base.
Yeah.
Now, we did talk about a base when we were talking about the digits and adding them up and getting a multiple of 3.
Yeah.
So somehow the base that we're writing in tells us things about divisibility by 3, or 4, or 5, or 6. It's sort of confused about 7, but it knows other divisibility rules, and those are just based on the base, right? I can't use the same thing to decide, look, the number 1101 in binary, if I add up the digits, I get 3. Is it a multiple of 3? No. So we have this property, certain things really do depend on a base.
On the base.
And how we write them down.
In this case, though, there are only 2 digits. Or do you count 0 as a digit?
In terms of...
Is it because prime is only...
You mean in base 2?
In any base. Do you count 0 as a digit?
Yeah, 0 is a digit.
So, oh yeah, okay. So,
I can put a 0 in a number,
Yeah,
right? I
yeah,
have the
yeah.
number 100, that's
For
a 1
sure.
and then 2 zeros. And it's different than the number 1 or the number 10.
yeah. So in base 2, if you do this whole thing where we were adding the digits and then adding them again until you have a single digit, there's only 2 options.
Sure.
So,
And in fact, for this number 13, I got 0.
so I'm guessing it would be, wait, do you have to, oh yeah, you would have to add in binary.
You have to add in binary, yeah.
So
I get 1 plus 1 plus 1, that's 3.
Yeah.
And then I write 3 in binary, that's 1, 1.
Mhm.
And then I have a 1 plus a 1, that's 2. And then I guess at this point, do I write 2 in binary and I get 1, 0? In which case, I feel like every time we add up all the digits, we'll always end with a 1. Or,
But you just ended with a 0.
well, I did a different trick.
Oh.
I was adding mod 2.
Oh.
Or I was adding as though we were in the field with 2 elements. So I think this process, and now here's a new conjecture. If I write down any binary number, I sum up the digits. I write that number in binary. I sum those digits. I write that number in binary. I always get 1 at the end.
What about 1, 1?
Okay, if I take 1, 1, 1 plus 1 is 2. I write 2 in binary. That's 1, 0.
Oh. Okay. Yeah, no, that makes sense.
Well, it doesn't make sense.
'cause
So
no
why?
matter-
Why
No,
should
well,
this
it
work?
doesn't make sense at all.
No, it
Like,
does it makes sense now because that's the only because if you start with 3, then you're gonna go down to 2,
Right.
and then above that anything just goes down to 2.
Does it? How do we know we don't get it something else? So number theory is famous for these types of problems.
So it's very logical.
Easy to
it's very
state.
It's very easy to state, but it's a thought and a half.
And like we can check with small numbers, right?
Yeah, but you'll never.
But there's always infinitely many
Yeah.
numbers. There's always so many numbers.
You need to provide like a induction situation.
I mean, we need something.
Yeah.
We don't necessarily need an induction, but we need some reason why we believe it. And it needs to be airtight. That's the hard part. So you've probably heard of the Collatz conjecture.
Yes,
This
actually,
says-
no, I have heard of that. I do not know from where, but I remember seeing the word. Okay, I don't know. I can't explain what it is, but I've heard of it.
So you can take a natural number and do a certain process to it. If it's even, divide it by 2. If it's odd, multiply it by 3, and then add 1.
Oh, and then you see where it goes.
And then you see where does it go.
But and then there's always like these loops, and like the conjecture is that every single number goes into this one loop where it's like 1, 6, 3, 4, something like that. Yeah.
Absolutely.
But we don't know if there's one
Right.
loop that's up there that just
That's
stays. Yeah. That's crazy. No, that is crazy. Veritasium has a video on that actually.
I think that's where I know it from. I think that's where I know it from. Actually, I think that's probably where I know it from.
Explains it very well.
So maybe I have some surprises up my sleeve.
Oh,
Which is-
did you solve it?
I know secret things about the Collatz conjecture.
All right.
I know if we generalize it, let's say we change the rules. Instead of divide by 2 or multiply by 3, add 1, we let ourselves say, okay, if the remainder is something mod 5, then we can put 5 different rules for what to do. If it's a multiple of 5, maybe we divide by 5. If it's 1 more than a multiple of 5, maybe I multiply by 4 and add 1. I can pick some different rules. There are sets of numbers, we only need 12, where it's undecidable if every number goes to a loop or not. So this Collatz conjecture problem could be, well, it's in a family of problems where we know some of them we will never know the answer to.
And that's just a property we just can't know the answer to.
We cannot know the answer.
Oh.
That's crazy.
Is it because it's too general? There's just too many different rules you can assign?
It's really built into the formalism of mathematics. And these are also relatively recent results. When people started writing down axioms for deducing things, mathematical proofs in the early 1900s, we had questions about, can we answer every question? If someone gives you a statement, can you say for sure if it's true or false?
Isn't that like a huge? I know this. We've already spoken. I've already spoken about this. Where like if oh no, there's definitely a thing.
It's
like
a millennium problem.
yeah, I think it's. I'm pretty sure it's a millennium problem.
Be
Is
able
it
to
not?
tell if something is.
Like, how do you know that that you can be able to tell the answer? Like, is there a way where you can tell if a problem does not have an answer or something like that? And there was a problem that I swear this was a problem that we spoke about. Again, I can reference it in a second, but it's not on the top of my head. But anyways,
Okay.
yeah. Anyways, yeah. So you were saying a problem where you don't really know about the answer or the solution.
Right.
Yeah.
Then like we can make statements, mathematical statements like every number eventually goes into this loop in the Collat's problem.
Mm-hmm.
That's a statement. It might be true, it might be false. There are mathematical statements that are true that we cannot prove.
And we know for sure that we can't prove
We
them.
know for sure we cannot prove
Wait, how
them.
do you prove that you can't prove something?
Good question. That's a very hard result. Okay, maybe I shouldn't say it's a
was
very
the
hard
whole thing.
result.
No, that was like the whole thing of this,
But
right?
it's very clever. And it had been a bunch of work throughout like 1930s with Turing and 40s.
Gödel's incompleteness
And
theorem.
Kurt
That was it.
Gödel
That was it. That was it.
is a
That was it.
fundamental decider of these problems. So Hilbert wrote down a big list of problems in 1900, David Hilbert, and Gödel half solved this one,
Mm-hmm.
just saying like, we can't do this. Along with Alan Church and Church's thesis that is like foundational to computer science that tells us things about if you have some algorithm and you plug in something, how do you know if it stops or not? Maybe it is just taking a long time and it will eventually tell you an answer. Or maybe it's stuck in a loop.
That's the halting problem.
It's
Very
exactly
similar
the
to the
halting
halting. That's
problem.
Turing's halting problem. Very similar.
So,
Yeah, we had a whole thing on this. Yeah.
the way that we show that certain things are undecidable is to create a halting problem out of them. And say,
That
if we
makes
could
sense.
decide this for all of these possible inputs,
Then
then
it
we
should
could
not.
solve this halting problem.
Yes, exactly.
And we
So it
know
should
that we
not halt.
can't solve the halting problem, so there must be some inputs where we cannot answer these
Okay.
questions.
Yeah, so that was literally the incompleteness theorem. So
so
we
you
had it
just-
on the Turing episode.
So you
I remember
have
it
a
now.
problem
I
that you
remember
know you can't solve, and then you just make your problem look like that problem,
Yes.
and then you say,
And our favorite problem is the halting problem.
The halting problem is a classic. Like, how would you put it in itself?
It is
Yeah.
the problem that we know that we can't solve. And so
That's
we turn
crazy.
our other problems into that problem.
Are there any other problem, like a problem that we know we can't solve, but is just fundamentally different from the halting problem?
Well, all the millenniums.
That's not a question for me.
Talking
But
about, we were
I
talking
think
about
the answer
primes.
is no.
We were
I have
talking
not
about,
seen one.
Wow.
We were talking about primes, so I wanted to ask if there's any knowledge that you have on the Riemann hypothesis, or the Riemann, or
Oh boy.
however he said. Because I know it's a very complicated way of describing it. We tried doing it on the Millennium Problems episode, but I don't think we really got the point across, because I don't even think we truly understood the zeta function, or whatever
Sure.
that's introduced with the Riemann hypothesis. So I know because we were talking about primes very recently, so could you have a quick on the Riemann
Maybe.
hypothesis?
I mean, I can
A
tell
quick
you
dabble?
some
'Cause I
things.
know, because we're talking about problems that can't be solved.
I can maybe
And
tell you
we're
why
also
we
talking
care.
about primes.
And in
So
fact,
think
I
it's
can
perfect.
tell you that this problem is not in the realm of problems we can't solve.
Wait, Riemann hypothesis has been solved, though, right?
No.
Or
But
isn't
it's
it one
solvable.
Of the, it's solved.
We know it has an answer. It is not an undecidable
Wait,
question.
so do you know if there are? So every question that has an answer, you know that it has an answer.
No.
That's okay. So exactly.
But
so
some
you don't even
questions-
know that. Oh damn. Okay.
Some questions,
Okay.
because of like
Yeah.
the way that we can formulate them, we can say we have this many quantifiers. We quantify over certain sets. By that I mean I'm saying we're asking, is this true for every element in a certain set? Is it true for every subset of a certain set of something? So we can write down like a formalized statement, and then we have families of statements that we know are all decidable. So the Riemann hypothesis is a question that's decidable. P versus NP, we don't know if it's decidable.
Oh, so we don't even.
So there
know.
is a millennium problem where we might never know that there's an answer to this question.
So we don't even know if an answer could be found. Damn, that's just on a new level of not knowing.
A Navier-Stokes equation is a similar one to this. We don't know that there could be something
That's-
like this.
Does it scare you as a mathematician, or I actually want to know just your opinion on this as a mathematician, like the fact, because I know because everyone has different answers to this, but that the fact that there are answers or questions, sorry, that don't have answers or cannot be answered? Like you were mentioning previously about, like we know this can't be solved. Like, is that unsettling to you? Because I don't know, someone who's, like in physics, for example, like you say, I mean, there's nothing I don't think in physics that, well, I guess Navier-Stokes, but there are like most things in physics, at least you know, okay, I don't know it, like dark energy. I don't know anything about it, but finding something out, like anything that I do find out about it will just improve the knowledge of dark energy that we have. But in something like math, you don't even know if it can be solved.
No,
Right.
sometimes you do know.
Sometimes you do. No, but the question that I'm asking you is, as a mathematician, is there ever like an unsettling feeling that you have that you're like, oh, this can't be solved? Like, I want to figure something, or like anything like that? Or are you just happy or content
I guess I
with the
used
fact
to.
that, yeah.
I used to have a perception that like mathematics exists outside of human construction, that is somehow universal. And at that point, I would think, well, not having an answer and knowing that we can't have an answer is like a flaw in mathematics.
Exactly. Right?
That's a problem.
Exactly.
Yeah.
But now I think math is just a human construct. We just make up the rules. And we have made up some rules to describe numbers. Within that set of rules, there's questions that we can't answer. And I
That's
think
just
that's
a-
fine.
Wow,
Yeah,
that's
that's just a-
totally a different
it's
way
just
of thinking
it's
about.
a property of what we defined.
No, but that's a totally different way of thinking about, what
Well,
can
I
be
think the
answered
difference
and what can't be answered.
The difference is because in physics, when we see something that we can't explain, the difference is that we see it happening, and so we know there's an explanation.
Yeah, so exactly.
That it doesn't necessarily make sense, but there's an explanation that can be
Exactly.
formulated. So
Or we can
Yeah.
dig into why is this
Yeah.
thing happening. You can
Yeah.
keep asking why.
yeah,
All right?
because you see it happening, so you know it's happening.
Yes.
You know it's there. So
Yeah, in math, you don't even know
Yeah,
if that's
you don't
true.
know-
You
you
don't
don't
even
know.
know if what's happening
Yeah.
is happening. At least in physics, you can see something happening. So there's always that connection to, and this is what bringing back to the original, that connection to reality that physics has. That, the lack of math, that it's all kind of abstracted, which I always find in general just interesting about, people who get into high levels of mathematics, who, like, I just love to, tease their brains, because I don't know, just the way that pure mathematicians' brains think is just in a way that's so rigorous, because you're not looking at the world or at least the way I think of pure mathematicians. Again, you can correct me if I'm wrong.
Sure.
But you're not looking at the world in terms of how can I apply it, but you're looking at it in a very abstract method. Like you're deducing like properties of, you know what I mean? Like you're not directly applying what you're learning into the real world, but more or less you're taking into the real world, you're trying to generalize it to any world, and you see what happens out of that. It's like a brain puzzle. Like the way I view math is just trying to work out your brain. It's like a nice fitness routine for your brain. And then where do you apply it? You apply it in physics. Obviously, this is every physicist's thought. But like this is where I see math. So like where do you see math? How do you see it differently than I do?
It's just a lot
or do
of
you see
fun
something?
brain puzzles that we can give to each other. It's say like, hey, have you ever looked at this? Have you ever thought about this?
I guess number theory would be a
And then you
big
get to
part
think
of just
about a
brain
thing, and
puzzles,
then it's
right?
fun.
Yeah.
And when you realize why, then you get this surge of excitement, and you go, oh,
That's why.
now I understand.
Yeah.
And then you make another one. And then you share those things with other people. And that is very much a social construct.
Mm-hmm.
That we're doing math because it's enjoyable. And because we get to share it with other people.
Damn Newton.
and then all the cool things that you figure out, the physicists go, oh, let me use that real quick.
Sure. I mean, that's nice for them.
Yeah, no, it is nice. It's like a donation box. You can just pick from.
No, because I mean that's where we get all our stuff from.
Oh, yeah.
Like all of our nitty gritty is from
100%,
math.
100%.
Like mathematicians provide a lot to the world, right?
Well, they're just like tools to help explain things that we see, and then we just pick the ones that help us.
Or I mean, I guess in terms of number theory, I mean it's not only things we see, but it's directly things that we've made. Like numbers are basically human.
Numbers
like
are just
literally
things we made up.
Yeah.
things that we made up.
Yeah.
Do you think, like in alien civilization, would discover or have numbers?
I think here's the thing. In
Numbers
in
in the
terms of
similar way.
number theory, the way you like, I think there would be some translation.
That's exactly
between
that's
the
my
two.
question. Would you, obviously in the numbers, like you wouldn't see one being written down in the same way, obviously. But my thing is, do you think that the theory part of it, like it's universal, of course. Like the numbers, no matter what you do here, will be the same thing on another planet.
So it's
somewhere else in the
interesting you say
universe.
universal to me. In like the 50s and 60s, mathematicians developed this way of framing a lot of concepts that is called category theory. And in category theory, we think about objects and we think about relations between the objects. They are like functions. So if you would like, you can think about not just one vector space like R2 or R3, but all possible vector spaces. Maybe you pick some field, you say all possible real vector spaces.
Mm-hmm.
And maybe you want just the finite dimensional real vector spaces. As a category, this is the same as the set of natural numbers.
Oh yeah.
That
Because you're just
Because
counting
you
up.
just
we're just counting up. We
Set of
say
vector space.
whatever vector space we have, we look at its dimension. That's the main thing. If two vector spaces have the same dimension, they basically look the same in this category.
Mm.
There's an isomorphism between them. So the category only knows the structure.
Mm-hmm.
And the integers provide this like universal structure that shows up in any kind of, the phrasing of it is a discrete dynamical system. Something, this is very much in the category theory realm, but something that we know will show up anytime we have separated objects that can map to themselves. So if I can define a function that inputs a natural number and outputs, or inputs an integer and outputs an integer, or inputs something and outputs something from the same area, and that area is discrete, that is, there are points that are not right next to each other. We can separate them out
Mm-hmm. By like a finite ball.
by something.
Yeah, by an
Like
epsilon
somehow
ball,
they're
yeah.
not crammed up. That gives us the integers. So that the integers will appear whenever we want to do some very simple things.
But hold on. If you need this idea of separation between the numbers, that means you need to have a notion of like things being in between and then there being distance between the two.
Or at least that there is some way to separate.
But why can't you just say that the integers are right next to each other?
Sure. I mean, we can. We
Exactly.
probably wouldn't call them integers.
No, you wouldn't, but
It wouldn't be discrete anymore. Right. The whole point of
no, but in the just when you think about integers, you say there's one and then there's two and then they're separated. But separated like by what, you know?
Aha.
Just nothingness.
So I guess the framework is if there is anything that can be separated, we don't need to know that they're integers. Just something that can be separate from something else.
yeah,
that
my
concept
brain just going to
exists.
237 like right now, like an epsilon ball around something. And if it's an epsilon ball, if it's not contained in the epsilon ball, it's discrete. That's just my. I'm just having such a proof level.
You can separate.
Yeah, you can separate.
maybe
Sorry, or they're
separable.
separable if it's not in that ball. But yeah, that's how I would think about it.
So, yeah, all we need is this idea of things being discrete, and the idea that something you can input something and output something else, and together those two things give us integers, so that integers are somehow universal in that sense. But that's not really how I think about them. I just like a cool pattern. I like to look at a list of numbers and go, "What's going on there? Can I explain this?"
I guess if you
So-
then they would be universal. So then you do think an alien
Yeah, so
civilization. Yeah.
so the aliens would have some notion of integers.
Exactly.
Sure.
There you go.
Exactly. Okay, we got that.
Perfect.
We got that. Aliens would be smart.
They
Aliens
can
would be
answer
smart.
this question about what do you get when you add up all the digits of the factorials?
Because there's something so... Okay, I think the idea of a unit is universal. Like, you can't... I mean, of course, we are humans on this planet speaking from what we know, but...
We can't really talk about universal.
If you start describing things about the world around you, you're automatically going to have to be like, there is one of those things. Like, eventually one will come up, and then...
And if one comes up, you can just put another one of those and say, hey, there are two. So I think...
That's what I think.
I think the origination of numbers are pretty obvious. Like, I think that would happen universally speaking. But...
Well, from our perspective,
From
like
our perspective.
I know. It's also weird to say because
As-
it is all from our perspective.
as mammals and as animals,
Yeah.
we can manipulate
Definitely.
the environment.
Definitely. As people who have eyes.
No, what do
and
you mean? I
ears,
mean, I think... Okay, yeah. Well, I think... Like, even fish,
You don't need eyes
for
and
example.
ears.
I think fish...
You don't need eyes.
No,
and
you don't
ears.
need them. But I'm saying
Okay.
everything can probably tell 1 versus 2.
Can it?
I think this is a difficult question in practice.
Yeah.
Like, if you're a mushroom,
Yeah.
and
Still
if you
alive.
see a couple of mushrooms,
Okay, I guess that's a different...
are they the same mushroom or not? And you might need to go underground and see if they're connected.
Is it connected?
And maybe the scale of it is just so enormous that it's impossible for you to tell if any two are actually the same organism or not. Like, in practice, you wouldn't be able to tell. Could that mushroom tell?
Oh, because he's a part of it.
Right.
So he would know,
And a mushroom's probably not a he.
right?
I mean,
No, that's
you would know.
you know,
It would
the
know.
mushroom
They,
would know.
the mushroom, does the mushroom know? Does the mushroom have a concept of discrete? And that I would say, I don't know. So maybe there's like alien forms that are all like mushrooms.
Oh,
Why not?
they don't need to count discreetly. Well,
Well,
maybe not to. Like, I feel like counting is. I don't know actually. As something that's alive and that tries to describe things, I feel like you need a unit.
We're not only alive, but we're also intelligent, which is a big difference between us and
Okay, well
mushrooms.
I think that's within the category of wanting to describe things.
Yeah, but why would it, no? But I think us describing things would be more necessary than a mushroom needing to do the same, because we are not only intelligent, but we can control our surroundings. Like, we can actually do things with knowledge of the fact that two things are different. What will a mushroom do? Hey, I'm different. Okay, I'm just gonna continue sitting here for the rest of my life. Like, at least we can be like, okay, this is different. Let me go do something about it. Let me get one more, or you know what I mean? Like, I can. Like, as intelligent beings, I think it is a little bit different than non-intelligent beings.
You may want to pause
think of
the
the same thing.
recording stuff.
Oh no, that's all right. That's probably the storage. We can still
It
continue
says
just talking.
full.
Yeah, that's probably just we can just still. Yeah, so the mushroom, probably, my thought of it, is still does not even need that knowledge. So it's not really important. But for someone like us and someone like intelligent alien civilization, I can see them needing something like
Okay,
this.
but what if the aliens are the mushrooms?
No, then that's what I'm saying. Then there's no
Oh,
point.
there you go.
Then there's no
So-
point.
Do we need to know about natural numbers?
I think so. I mean, of course, we could just not do math at all and not count things at all. In that case,
It's an option.
in that case, we don't need natural numbers.
So maybe we don't.
Yeah.
I guess.
But it's a useful thing. I guess we want natural numbers.
I guess it depends on the usage. I guess everything that we really make, I mean, humans, if you think about it, like we make everything, the whole idea of math started because we just wanted a tool to help us do something else, is what I would think how it started.
That's interesting.
Because I would think it started, like the whole concept of mathematics would have started when you're trying to analyze some situation, obviously on paper, or at least I would think on paper. And let's say, like, for example, you have some numbers.
When do you think paper was invented?
Okay,
Yeah.
no, not paper like that. I'm saying, like, not practical. It's like, I'm saying, like, in your head, not, that's the distinction I'm trying to make. Not actual paper, not like you're writing it down on paper. But the point I'm trying to make is, like, I think maybe mathematics was first used when you're like, hey, I have a bunch of numbers or I have a bunch of things and I want to analyze something about those things. And you create a concept that we now call mathematics to analyze those sets of numbers, right? Which is what my thought would be how they originally invented.
I would say even to have a concept of numbers is mathematical. How do you get the numbers first?
I
But
guess
really,
even-
that like
even,
mathematics is a bunch of processes.
Even thinking of 1, 2, 3, even that itself
Sure.
is mathematical.
Yeah.
Yeah, that's right. So then mathematics would have started even prior.
And these things about logic, about if this happens, then this
yeah,
happens.
logic. If we
But
say
is that
math is
mathematical? Is that
logical and mathematical,
does that count?
it's here and there. It's kind of on the same, but it's not really. Right? Very questionable.
I don't know that it's questionable.
Oh, I don't know, because I don't know if logic, because I think logic is still rooted in philosophy. Now everything's rooted in philosophy, but I think math
But
comes
where's
out of the
philosophy
logic.
rooted?
Oh, where's philosophy rooted? I think philosophy is rooted in the human brain. Yes, that's my answer. I think philosophy is significantly rooted.
That's the worst answer.
You don't think so? I think philosophy
it's in the human brain.
No, it's rooted in the human brain. That means, like,
What does that even mean?
The root, where's the root coming from? It's coming from the thoughts that you have, questioning yourself, questioning your surroundings.
So you're saying thoughts are in your brain?
Are you saying otherwise? Thoughts are not in your brain.
You're saying thoughts are literally in your physical
Not
brain?
physically, man.
Well, there
Like,
you
come
go.
on,
So what do
I'm
you mean
saying-
by where?
Well, physically,
So
first
what
of all,
do you
yes,
mean
if
by
the
where?
neurons are firing in your brain, first of all. But second of all, like, the thoughts in
Is
general.
this like philosophy and
yeah, this is, yeah,
podcast?
significantly went into philosophy. But I'm just trying to say
Let me
that-
bring us back to numbers.
Yeah, no,
Yeah.
go ahead.
In number theory, I see some stuff and I go, why is that going on? So if I'm thinking about properties of integers or natural numbers, I want to look for different patterns. Maybe I want to look at primes. Maybe I want to look at square numbers. If I take any number and I multiply it by itself, any natural number, I get this pattern that goes like 1, and then 4, and then 9, and then 16, and then 25, and then 36. I get a bunch of squares. And if you want to have a physical description of it, you can say, well, it's the area of a square that has that side length. So maybe you care about it. But for me, I just want to know, like, what's going on with these? Can I say anything about them? And one thing I notice is sometimes 2 times a square is very close to another square. So like 2 times 4 is really close to 9. And 2 times 25 is really close to 49. Did I just miss by 1 every time? So I want to know, does that usually happen or is that unusual? And I can ask very similar questions. What about cubes? Sometimes I notice, okay, if I cube a number, that means I multiply it by itself 3 times. So like 2 times 2 times 2, that's 8. 8 is a cube. 3 times 3 times 3 gives me 27. 4 times 4 times 4, 64. Sometimes a cube is really close to a square. Like 8, really close to 9. I don't have any other examples, but does that, I guess 1 is really close to 0. Does it ever happen again? Does my other one ever happen again? Can I get 2 times a square to be within 1 of another square?
Are there numbers that are cubes and squares?
Are there any numbers that are cubes and squares? Let's go up a little bit more. First off, do Do you have a conjecture about this?
Oh, 64. We found it.
I didn't have to go much further.
No.
The next square on my list was
Yeah.
64,
Yeah.
which is 4 cubed. So maybe I want to go, wait a minute. What numbers are on the list that are the same numbers? There's 1 and 1. That's a cube and a square of 1. 64 is a square of 8 and the cube of 4. Are there other numbers on that list that are the same?
There must be,
Why?
because it happened so early.
It happened early, so
Yeah.
you think there must be.
Yeah.
Okay.
What a form
Of these 3 questions, one of them I think you can solve right now with what you know. One of them I think you can solve, but it will take a little trickery, and I might have to tell you about algebraic numbers. One of them you can't solve. We know the solution. It's very complicated. 2 answers are there's infinitely many. One answer is there's only this one example. And they all happen pretty early.
What were the questions again?
Can you find a square that's also a cube?
Yeah.
Can you find 2 squares where 2 times one of them is within one of the other?
Yeah.
Can you find a square and a cube that are close together, within one?
Okay, I think that there are, like the answer that was there are a whole bunch at the beginning is the one that they're 1 apart in the squares.
Okay.
And
So we had these examples. The square 4, 2 times 4 is within 1
Yeah.
of 9.
yeah.
And then 2 times 25 is within 1 of
Yeah.
49.
The reason why I think that is because the distance between square numbers just increases so much that if you multiply one, like an earlier one, by 2, it's going to be like somewhere in the middle, but just very far away.
Okay.
So it'll just happen less and less as
Okay.
you keep going.
So what about, I mean, this is a good motivational idea. It should happen.
Mm-hmm.
They spread out. If you double one of them, it's going to fall in between some squares, and once in a while it will be right next to one.
Mm-hmm.
What about cubes versus squares? If I look at all the cubes, the squares are still spread out the same way. Now when I'm cubing a number, it's going to fall in between some squares. Does it ever land right next to another one?
Eventually,
Okay.
it's spread out, but even more spread out than the first question.
But there should be more,
Yeah.
right? We found one really early on.
Actually, wait, this might be like some type of rational, irrational type thing where it's just so spread out that it just never happens. I don't know.
Yeah, my mind's just thinking this whole time. I'm just trying to come up, but I don't think I can.
Because the cubes spread out way faster than the squares.
But sometimes they land right on them, right? Like 64 and 64. Do you think that there's a bunch of cubes that are squares?
I was thinking about the relationship between
yeah.
the 64 and 64, and
Yeah.
I'm like, okay, 64, it's 4 cubed, and this is 8 squared, and I'm like, okay, think about some relationship between 4 and 8. But that doesn't really apply to everything, because then I did another example with like
Yeah, so
2
we're
and
talking
4, and that
about
doesn't
like
apply.
we're trying to solve like for what integers is like m to the n equal to n to the m.
With some combinations.
Basically.
I feel like it's
A to the B
infinitely.
is the same as C to the D.
This sounds like
Yeah.
such an Olympiad
But
problem.
I feel
we
like
have
it's-
we have some fixed parts, right? We want like A to the 3 equals B to the 2.
Oh yeah.
8 to the 3
Oh, that's what we're trying. Yeah,
Right?
that's yes.
equals B yeah.
We want a cube that's also a
And
square.
we want to find the values of A and B, exactly.
I don't know. I want to say there's infinitely many, but that just contradicts what I said earlier. So, I don't know, right?
Because what we're doing, I mean, if you put it just algebraically like that, like what you're doing in this case, so you're just gonna have. I can't think of an answer. Like I can maybe think
Can you
about
find
it,
another
but-
example? So this is the next thing that I would do. Like, as a number theorist, I look at these things.
I would find
and
the
then
next
I go,
example, but I'm not trying to like think about that.
Python,
But
tell me.
sure, I would probably do that.
Make a computer do the work.
Yeah, for sure.
Something can compute a bunch of squares for me. Something can compute a bunch of cubes for me. And then it can just tell me what the numbers are. Do you want me to give you an example?
I mean, if you have one on the top of your head.
Sure. How about 2,187?
Wait, that was on the top of your head?
Yeah.
What's on the top of your head?
Everybody knows. I know I'm worried that I picked something that is not going to work.
Red.
But I think that this is. Oh, never mind. I can make an easier one. 729.
Obviously.
729. That's 9 times 9 times 9. So
Sure.
it's a cube,
Oh, but
right? 9 times
yeah.
9 is 81.
Right.
8 times 9 is 72. Okay.
But 9 is also 3 squared.
So what?
So it's like 3 times 3 times 3 squared.
Okay, so it's 3 times 3 times 3 squared. So it's also 27 squared.
Oh, so there are infinitely many. Because
Why?
you can just pick any number, or let's say you pick any number that is not prime, and what you can do is just write it, like multiply it by itself n number of times, and then what you can do is just say, okay, wait, no, sorry. Let me reset that. You pick any number. You pick any number that is composed of squares.
So a square.
Yes.
Okay.
So no, you take a square, you multiply it by itself n times, and then that's also going to be the same thing as just decomposing it into what its base, is that what it's called? The number
Maybe
that you
square root?
Oh yeah, you decompose it into its square root, and then you pull out the square, and they say that number is also a square. So it's a cube and a square.
Okay.
But
that only works
n
for
times
numbers.
It's
was
right-
3 times.
But that
right?
but that only works for cubes that have that are
No,
squares.
it doesn't. Because I can say that 9 times 9 times 9 times 9 times 9 n times.
Yeah, but 9 has a square, is what I'm
yeah,
saying.
but I said that at the beginning.
Okay, so it works only for numbers with
Yeah.
squares. Yeah.
So,
So you-
Parker's algorithm is start with a square,
Okay.
multipy it by itself some number of times. Like
Yeah.
if you want to get a cube, multiply it by itself 3 times.
Mhm.
Then you know that number is a cube
Yeah.
because you multiplied 3 times. You also know that number is a square because if you take the square root of your original number, you can sort of pull that part out the n times. So there's a proof.
Infinitely many.
There's infinitely many cubes that exactly hit a square.
Yeah, because if yours has infinite, then others obviously.
That's surprising.
And let me tell you, there's only this one example of a cube that's 1 less than a square. And aside from like 1 and 0, there's no examples of a cube that's 1 more than a square. They never get close again.
That's just
This is a result from 19 years ago. In 2002, we
That
had-
is so recent.
so they.
Oh my god.
They
Wow.
hit the squares infinitely many times, but they never go 1 over.
They never go,
That's crazy. That is crazy.
and they only once go 1 less.
Wow.
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 So
That's really something.
that's by a Romanian mathematician, Mihalescu, and uses a lot of techniques from algebra.
Man, if that doesn't get you to like really understand or love what number theory means, I don't know what will. That right there was the
100%.
intuition required. That was deep.
Sure.
No, yeah, I can definitely see the appeal.
So
'Cause,
at the
yeah, I
start
can
you asked for
definitely
like, what
appeal.
are some big theorems? And I would say a really big theorem in number theory is that if we take some kind of an equation with cubes and with squares, or just with cubes, that there's a finite number of integer solutions. So this question was asking, can you find any a cubed minus b squared equal to 1 or equal to minus 1.
Mm-hmm.
And that this equation only has one solution is a surprise. In my research, I look at things like, can I take 5a cubed minus 7b cubed and get some number? What's the smallest number I can get by plugging in integers? Sometimes it's 1. Sometimes it's not 1. Sometimes it's bigger than 1. How much bigger?
Mm.
And then I want to know, can I tell just based on the coefficients? Can I make it really big?
Mm.
Can I put some rules that say the only way that this has a solution is if that number is big? That somehow 5 times a cube and 7 times a cube are always kind of far apart from each other.
This might be an obvious question, but is there an upper bound to the separation between cubes and squares?
Like how far apart can
Yeah.
they be?
Yeah.
I'm not sure what you mean. Can I clarify? Okay, if I pick the example of 1, if I said 1 squared, are you asking, can I find a cube that's really far away from 1?
No, I'm saying if you just plot all the squares on the number line and all the cubes, is there an upper bound to how far they can be from each other? Like if you pick, if you say, here's a cube.
Oh, like the closest one
Yeah,
to it.
the closest one.
That's a very good question.
Yeah.
I don't know that this is known.
I just created a problem.
Here's what I know.
Wow.
Here's what I know. Let's see. Yeah, I don't think that this is known.
I'll look into that.
So we have some generalizations of like Michalescu's theorem now. Can we find all the cubes that are 2 away from a prime, or 3 away from a prime, or 4 away from a prime? But I don't know, you're asking, is there a certain number, like k, where there should be infinitely many cubes that are within k of a square?
Yeah.
I don't know that this is known, and I think that the answer will be no. That
seems like a very specific, but also I can definitely see how that problem was inspired by exactly what we did. But yeah,
But yeah, good question.
that could definitely. I think that can be that could be thought about as a proof.
No.
No.
That's not a proof.
No, it's a
But
question.
like, but
We have
I
a
mean, but it's-
conjecture.
Yeah.
We
No,
have-
but it's a conjecture to prove.
Oh, yes,
that's
yes.
what I'm
It's a
saying.
thing
Like we need to prove this.
We do need to prove
That's what I'm
this.
saying. That's what I'm saying.
Welcome to number theory.
Yeah.
Welcome
We see
to
some
number
pattern and we
theory.
go, what else can we ask about it?
Yeah.
And now we want to think about proofs. And then we go to the other fields of math and we say, what can you tell us, please? We're desperate. We need to know these things.
Yeah.
It's very important to us that we have a proof. And then they're very kind and they give us their tools. And we say, thank you.
Maybe this is unsolvable.
Maybe.
Maybe there's just no solution. The
I feel like I can put it into the framework where we know that there's a solution.
Okay.
But maybe it is unsolvable.
Well, that's the art of number theory. I mean, super powerful. I mean, I can clearly see where it can, I think, be used in such a general case too.
See, I don't know that number theory can ever even be used. Like
No, but used in a sense where you can ask yourself like the basic stuff about, like anyone can think about.
Yes.
It. Like it's not like something that like a third year PhD level mathematics student can think of. Like even a non-mathematics student can read it and be like, huh, that's cool.
Yeah.
You know what I mean? Like it's a very readable question. It's very analyzable answers. I mean, in ways that I guess are not really from number theory, but like there's still questions that can be understood and appreciated.
I guess we
by the
can
general
answer
public.
this question. We can say 0.
0.
There's a whole bunch of cubes that are within 0 of a square.
Yeah, but that's the lower bound.
And you want to
The
know,
upper bound. Is there some number, k, such that there are no...
that they're infinite?
So, you pick cube. They say for all cubes, there is no square that is directly after or directly before it that the distance between it and the square is greater than some number k.
Okay.
I don't know.
Now you've formally stated your conjecture.
Yeah,
Now you have this. And now maybe someone will solve it for you
Yeah.
and then tell you.
that'd be nice.
Well,
Put it in the comments. It'll be comment of the week.
Yeah.
yeah,
That'd be
let's see
cool.
it. Of course, if someone solves that, comment of the week for sure.
That'd be crazy. So yeah, I guess on that note, it's been 2 hours.
Yeah, this is actually officially the
yeah.
longest podcast we've ever
Longest
recorded.
podcast.
Cut it up.
For sure.
This is beautiful. No, we actually do not touch our podcasts because we like to keep it
Yeah.
like raw. We like to keep.
What a mistake. You can get 2 weeks episodes worth.
Oh well, I mean that would be cool, but no, not the point. The point is just whatever conversation we had, just gonna stream it raw and
For sure.
enjoy it for all the listeners out there.
For sure.
So well, to the listeners now, hope you enjoyed it. Anything that we want to say? Just the usual.
If you're still listening to this episode right now, make sure to follow us on Spotify or YouTube or anywhere else.
Really anywhere.
Drop a comment.
Yeah.
Thank you so much.
We're almost at 2,000 YouTube
welcome.
followers. Oh, I didn't even say this. We're almost at 2,000 on YouTube, bro. Like, I think we're like 20 something away. So like we're super close to the big. Oh no, sorry, not 2,000. Yeah, 2,000. We're not at 3 yet. So get us there. No, okay. So if you're obviously listening on any platform, why don't you head over on YouTube, go watch the video, just see our beautiful faces, smash that like button, just for the algorithm, and comment as always for the comment of the week.
Yeah.
So, as always, thank you guys for watching. Thank you, Dr. Zack, for even coming on here today. It was a beautiful conversation, beautiful place that we're in right now.
You're
I wish
welcome.
we could kind of have a 360 of all the whiteboards or the blackboards that we're looking at. I don't think we can understand a single
Nope.
letter.
Nope.
Not a single
Not
one.
even a letter?
Not a
There's
single
G
one.
there.
Not a single one. Like, you know what I mean? Like, in the context. Like, not a single letter. But anyways, thank you for listening. Thank you for watching.
All right. This has been episode
86.
number 86. Yeah. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.
See ya.